Section 5.5, the binomial distribution. Alright, in this video I want to introduce a new formula called the binomial distribution, but before we can get to that I need to show you a new function of your calculator, which is called combinations or binomial coefficients. To write them out, it looks like a fraction where we forgot the fraction bar, but it's not n over x. We would read this as n choose x. And it represents the number of ways of choosing x objects from a set of n objects. So if I'm going to calculate 8 choose 3, I can do that on the calculator, and I'll show you that in just a second. But what it represents is if I had a group of 8 things, let's just go ahead and make that little group over here, and I was going to choose 3 of them, maybe this one, and that one. That's one way of choosing 3 from the group of 8, but how many different ways are there that are possible? And it turns out there's perhaps more than you might think. But the way you calculate that on the calculator is fairly simple. You have to type things just like you'd say them. So since this is 8 choose 3, we're going to hit the 8 key first. And then for choose, we have to hit a couple buttons. We have to hit the math button, and then go over to the probability menu, and then the choose is the NCR right here, number 3. So I've done the 8, now I'm doing choose, and then I would type the 3, and it would tell me that there's actually 56 different ways of choosing 3 things from a group of 8. And that, by the way, is even when I don't care what order they're in, but just which 3. So that is also if I count this one, and that one, which may not have been the order I circled them in originally, I wouldn't count that as an additional way. So that's one, and there's 55 others like it. If I do 8 choose 55, that should be the same answer, because when you choose 3 to circle, there's a sense in which you also chose 5 to leave uncircled. Well, let's go ahead and verify that on the calculator and get the extra practice. So 8 choose 5 would be 8, and then math, and then probability menu, and then down to number 3, which is choose, and then put the 5, and I expect to get that same answer of 56, and that's what happened. Alright, and then just some other things to show you kind of the power of this. If I had 52 choose 5, there's 52 cards in a deck of cards, there's 5 cards in a poker hand. So if someone was thinking, if I shuffle up a deck of cards and just dealt somebody 5, that would be a poker hand. How many different poker hands are there? And to do that, I would just do 52 choose 5, so 52, math, probability, choose 5, and I get that there's 2,598,960. And so that kind of shows you some of the amazing capability of this choose to do some counting for us. When we're doing probabilities, a lot of times we have to count different options, and this is something that can count millions of things very quickly for us using this formula. 51 choose 6, some state lotteries used to have 51 numbers, and then you would choose 6 of them, and then they would choose 6. If your 6 matched theirs, you would win the jackpot. So how many different possibilities are there for 6 numbers to choose? 51, math, probability, choose 6. It turns out there's 18 million different possibilities. So if you were in a state that was like this, where there was 51 numbers and you chose 6, then you would be choosing one possibility out of 18 million, and so your chance of winning that lottery would be 1 in 18 million. So it's pretty amazing that this little choose item here allows us to quickly count up the 18 million different possibilities in the lottery and therefore figure out the probability of winning the grand prize. And you'd think that would be super complicated, and it sort of is, but not if you have this tool to help you out. And then finally, 100 choose 12. 100 choose 12 might be a situation where you get 100 people together for jury duty, and you're going to choose 12 of them to be on the jury. So how many different possibilities for juries are there when you're choosing 12 from a group of 100 who have come in for the day? So that'd be 100, math, probability, choose 12. And we get what at first seems like a strange answer, 1.05. We've gotten 56 and 18 million and 2.6 million. Now all of a sudden we get a decimal, 1.05. But actually, if you look over here at the E15, that's scientific notation, which means we have to move the decimal to the right 15 places. So I'm just going to write down that this is very big. And that may seem like a strange thing to write. If you want to, you can move that decimal 15 places over. I believe it's 1,050 trillion, or 1 quadrillion, roughly, different juries that you can form. You might wonder, like, what are we supposed to do on homework when we get a number this big? But it turns out these combinations are just a small piece in a bigger calculation. And by the time we get to our answer, this big size will have gone away to result in a probability that's between 0 and 1. So don't worry about how to write these, but that would be moving it over 15 places. And again, you might want to write this one out, and when it says E72, you're probably not going to want to write that one out. So we won't have to in the situation we're going to be using these. Alright, so the situation where these combinations are going to be handy for us is in something called repeated identical trials that are called Bernoulli trials. And they're called Bernoulli if they meet a few conditions. One of them is they have to have 2 possible outcomes for each trial, and we refer to those outcomes as success and failure. So S for success, F for failure. And one of the things to know right away is that success and failure are just judged based on did we see what we were looking for. And strangely enough, human nature as it is, a lot of times we're looking for bad things. And so a success might sometimes be a good thing, it might sometimes be a bad thing. It's a success in the sense that we saw what we were looking for. And then that's one of the conditions to be Bernoulli. Another one is the trials need to be independent. So your chance of success on the 4th try can't be affected by what's gone on the previous 3 tries, and so on. And then the final condition is the probability of success has to remain the same from trial to trial, and we use a lowercase p for the probability of success, and these are the only 2 outcomes, and they're complements of each other. So if the probability of a success is p, then a probability of failure would be by the complement rule 1 minus p, but we usually use the lowercase q to represent that. But the way you would get q is to do 1 minus p. So the most kind of pure example of something that is repeated trials that could be considered Bernoulli would be tossing a coin over and over again. Each time there's 2 possible outcomes, success and failure. Well, really it's heads and tails. Which one's the success depends on which one you're counting. If I say I'm going to toss a coin 100 times and count how many heads I get, then heads is a success. If I say I'm going to count how many tails I get, then tails is a success. It could be either way. And the trials are independent on a coin toss, so what's happened, whether you get heads on the 5th try is not affected by the previous 4 tries, and every time you toss that coin, assuming it's fair, the probability of heads would be a half, and the probability of tails would be 1 minus that, which would still be a half. Other things that can fall into this that might not seem like they could at first would be something like taste tests. So if it's Coke versus Pepsi, that might seem clear there's 2 outcomes, but what if it's Coke versus Pepsi versus 7-Up? Then all of a sudden you have 3 options, but it can still be considered just 2 options if you kind of identify one of them as a success and everything else as a failure. So maybe if they pick 7-Up, it's a success, and either of the other 2 colas would be a failure. Similar for drug effectiveness, where if you took a drug to treat an illness, it might make you better, it might make you worse, it might just keep things as they were. And what a success would be might vary. You might consider success to be improvement. In other cases, you might consider success to be improvement or if things stayed the same. But as long as you identify one group as a success and everything else as a failure, you can still end up fitting this pattern. Alright, so there's our setup, and we'll move to the next page and look at an example. Alright, so as our example for Bernoulli trials, we're going to look at a situation where we're betting on red in the game of roulette, and in a roulette wheel there's 18 red numbers, 18 black numbers, and 2 green numbers, and all of those 38 slots are equally likely to have the ball land in them. And they ask us what would be a success. Now typically when I ask students this, they'd say, oh, if the ball lands in a red number, but that's assuming that winning would be a success. A success is whatever it is we're looking for. So before you jump to that conclusion, read what they're asking you to find the probability of, and they want the probability of 3 wins. So we are in fact counting wins. So a success would be if we win, and that would also mean a success is the ball lands in a red slot. And then what is the probability of the win? Well, there's 18 red slots, and the wheel has 38 numbers on it altogether, or slots on it altogether. If you divide that out as a decimal, you get 0.4737. And then for Q, you would just do 1 minus P, and if you do 1 minus, you get 0.5263. You could also say, if the red is a success, then everything else is a failure, which would be the 18 black plus the 2 green. And if you did it that way, you'd have 20 out of 38. So you could do it as a fraction or a decimal. Alright, so now let's try and find the probability of 3 wins in 5 plays. So they don't mention what order this happens in, and so one of the things we've mentioned before is if something can happen in more than one way, we need to figure out the probability for every way that it could happen and add them together. So 3 wins in 5 plays could be a win, a win, a win, and then 2 losses, where we win the first 3 and then lose the last 2. But it could be something like 2 wins and then a loss, then a win, and then a loss. So I've made a list here of every different possible way that you could win 3 out of 5. And then when you start trying to calculate the probability for each of those, these are independent trials. So the probability of success, success, failure, failure would be the probability of success times the probability of success times the probability of success times the probability of failure times the probability of failure, or P to the third and Q to the second. But if you pick a different one, like this one where you lose the first one, win 2, lose 1, and then win 1, that means it would be Q, P, P, Q, P. But this is a multiplication, and multiplication is commutative, which means that the order doesn't matter. And so that could be rearranged, and it's also P cubed, Q squared. And in fact, that's what it is for every one of these. And I said just a minute ago that if you're trying to figure out the probability of 3 wins, and there's many ways that can happen, you need to figure out the probability for each of the ways and add them together. Well, if every way has the same answer, then instead of adding that thing to itself 10 times, we can just go 10 times P cubed, Q squared. And then what we want to remember here in terms of the pieces, this is because we want 3 wins. And if you're going to play 5 times and have 3 wins, then there's going to be 2 losses. And then the 10 is the number of different ways it can happen. And every time we use anytime we're doing one of these success-failure problems, we're going to want to have all 3 of those pieces. Now let's go ahead and calculate this one out. So on the calculator, what that's going to look like is 10 times 18 out of 38 raised to the third times 20 out of 38 raised to the second. That may look a little weird the way I've written it down, but that's the way it's going to look in the calculator. And I did use the fractions instead of the decimal because the decimal has some rounding error in it, so I'd rather have the exact answer of the fraction for doing this work. So 10 times parentheses 18 over 38. That needs to be in parentheses before we raise it to the power. Otherwise you would just end up raising the denominator to the third. And then times 20 over 38, also raised to the second power. And then what do we get there? Approximately 0.2944. So we've just computed the probability that if you played roulette 5 times, betting on red every time, that you would end up winning 3 of them, and it's about a 29.5% chance. Alright, so what we want to do next is figure out how could we have figured out this 10 without having to list all the possibilities, because that's the part that even once you're good at this would be a pain, would be to have to list every way it could happen. I used a pattern here, but even then it's still kind of nerve-wracking to think, did I get everyone? Did I miss something? Did I count something twice? So, and it's annoying also to make all this chart, and all you really need from it is the number of ways, 10. You didn't really even need to see all the pieces. So to answer this question, let's jump down to the bottom and look at another one, and I'll try and talk you through it down here. So consider playing roulette 9 times and betting on red and trying to find the probability of 5 wins. So we're switching things up a little bit. It's 9 plays now, not just 5. And then instead of 3 wins, we're looking at 5 wins. So one of the ways this could happen would be that I could win the first 5, and then I could lose the 4 after that. And if I wanted to represent that down here, I could say that would be P to the 5th to represent the 5 times that I win, and then I would have Q to the 4th, because if in 9 plays I win 5, then there'd still be 4 losses. But if I just stopped right there, I'm not getting the probability of 5 wins in any order, I'm getting 5 wins in this specific order. To get all the different orders, if you look back up here, I have to multiply by the number of different ways that could happen. So I could start listing them. I've listed 1, I could start listing more. Win, 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 loss, win, loss, loss, loss. Now I'm up to 2 of them, but I'd have to make this whole list until I had every possibility. And however many different ways there were for me to do this, that's what would go out front. So what I want to do instead of listing them is think it through. So I want to think about having 9 plays, and then I'm going to choose 5 of those to be the successes, and then the losses would just fill in the other 4 spots. So I don't need to list them, I just need to think how many ways are there from these 9 blanks to choose 5 to be the wins. So listen to those words carefully again. I need to think about from these 9 blanks, how many ways are there to choose 5 to put the successes in. And the answer to that, as you might be thinking as you're listening to me there, is 9 choose 5. From the 9 blanks, we're choosing 5 to be the successes. So rather than having to list them all out, I can take the number of plays, 9, choose the number of wins, 5, and use that as my multiplier. So let's go ahead and write that out now. This is the way it would look on the calculator. 9 NCR, which is our choose, 5 times P, which is 18 out of 38, raised to the 5th, times 20 out of 38, which is Q, raised to the 4th. And let's go ahead and enter all that in. So 9, math, probability, choose 5 times 18 over 38 to the 5th times 20 over 38 to the 4th. And when I do that, I get the probability of 5 wins is approximately 0.2306. Alright, so we do need that answer, but I also really what I wanted to get there is the formula. And so it looks like the answer to that question up above, how could we have figured out the 10 without listing the possibilities? Well, on that one we had 5 different plays, and we were trying to choose which 3 of them would have gotten the wins. So it should have been 5 choose 3. Now if that's correct, we'll get the 10. So let's test that real quick. 5, math, probability, choose 3, and we do get the 10. So instead of having to list out all those possibilities, I could have just done 5 choose 3, and the same thing was true down here. Instead of continuing this list on, I could just do 9 choose 5. And by the way, that's a good thing that we have a shortcut, because 9 choose 5 is 126. So I only had 2 out of the 126 possible orders, so there was a lot more writing to do if I was going to show it all. Alright, so now we want to go ahead and take all of that and build it into the binomial probability formula. So here's our formula for success-failure problems. The binomial probability formula. The requirements for using it is you need n identical trials, so you have to be doing something over and over again, like flipping a coin or playing roulette. there needs to be 2 possible outcomes for each trial, but we've seen that's not as restrictive as it might sound. In fact, if you think about a roulette wheel as 38 slots, and yet we made it success-failure by saying either the ball lands in a red one or it doesn't. The trials need to be independent, and the probability of success needs to remain the same from trial to trial. If you realize you're in that situation, then here's the steps you want to do probability. First, identify a success, and that is whatever is being counted. So we counted wins, but somebody might decide to count losses. So whatever's being counted is considered the success. And then determine n, which is the number of trials, p, the probability of a success, and q, the probability of failure. And then once you have all those pieces, once you know n, p, and q, if you want the probability of x successes, then you would take the number of trials, choose the number of successes you want, times the probability of success raised to the number of successes, times the probability of failure raised to the number of failures, which would be the number of plays minus the number of successes. And if you look at that, that does work for this one right here. We had 9 plays and wanted 5 wins, so n choose x was 9 choose 5. Then we took the probability of success and raised it to the 5th power, because we wanted 5 wins. And then for the number of losses, we did 9 minus 5 and got the leftover 4, so that was n minus x right there. A few things worth noting. When we say that it's the number of trials, that's true, but it could also be plays or sample size. Those are common things that get used for success-failure problems. And then when we talk about the probability of success, this is in any one try. So when I was doing the probability of success down here for roulette, I didn't consider that I wanted 5 wins or 9 plays. I just said if I were to play roulette just one time, what's my chance of winning? 18 out of 38. So the biggest mistake people make when they're trying to figure out their N, P, and Q is for P to try and incorporate the N and the X in there somehow, and that does not apply. You just think, what if I only did this one time? What's the chance I would succeed then? And so if you go back and look at the top, we figured out the probability of getting a red number before we even knew how many times we were playing or how many wins we wanted. It was just based on what's on the wheel and how many of those were successes. Alright, so we're going to go ahead and see the rest of this on the next page.